Assalamu alaikum. This is lecture 13 on digital control system. We are discussing chapter 3, Z-plane analysis of discrete time control system. Topic that we are covering right now is article 3.7, a realization of digital controllers and digital filters. We already have gone through one lecture on it. This is the second one. So basically what we have covered up to is standard programming, direct programming and standard programming. So um, if you implement the pulse transfer function as it is, then it is actually known as digital direct programming with n plus m number of delay elements. So basically, so based on your equation, that is g of z, which is output by input and is given as a combination of b0 plus b1 z inverse goes up to bn z to the power minus m. Okay, so in the denominator we have 1 plus a1 z inverse plus goes on up to an z to the power minus n. So we have m number of zeros and n number of poles. So if we implement with n plus m number of delay elements, then we call that one as a direct programming. So if the block diagram is represented with n plus m number of delay element, then we call it direct programming. And if it is minimized, and which one is higher? In general, n is higher, number of the pole is higher. So that is why if we reduce it to n, then we call that one as a standard programming. Standard programming. So different other structure is available, and basically those are introduced because of the fact that three kind of error is available there. First error is the quantization error that we have seen, because we have limited number of digits, so limited number of discrete values we have. So whatever the analog signal is given, it has to be fit into that discrete values. So that is why quantization error is there. Quantization error. Okay, so in the chapter, I think in the one, we have discussed a bit about the quantization noise or quantization error. Then there is another error because of the round offs. Okay, so accumulation of the round off. So values closer to certain value, and because of that, we have to round off to a certain level. Accumulation of round offs, round off errors. Okay, this, and the third one is since we have these new parameters that is coming, AIs and BIs, and that are real quantities, and they will be also be quantized. And because of that, third kind of error is being generated: quantization of AI and BIs. Okay, so this third one can be minimized if instead of using the pulse transfer function as a large higher order polynomial in the numerator and the denominator, instead of that, if you distribute it in first and the second order and different structure, definitely we said it can be cascaded or in the parallel, or it can be ladder. So based on that, the quantization error of the real parameter AI and BI can be minimized. So from that idea, different structure has been used, which actually takes in account of, instead of a high order pulse order transfer function, truncating that into first and the second order pulse transfer function, and combination of that in different structure, like as I said, cascaded, parallel, and as well as ladder. So three standard programming is the structure is there. First one is called cascaded, or more precisely, they also say called series programming. Recently, I shifted from the Microsoft Whiteboard to the whiteboard available in the Zoom, because I'm not sure why the handwriting is not quite up to the mark in this one. But at the same time, it's a lot faster in the Microsoft Whiteboard. It was actually lagging a bit. Okay, so three kind of structure available: series programming, parallel programming, and ladder programming. Okay, so start one by one. Series programming, basically in the series programming, what we do is we represent the pulse transfer function as a multiplication of pulse transfer functions, gz1, g2z, and goes on up to say p number of them. Some of them will be first order, some of them will be second order. So based on that, we can actually write in this way. So multiplication from I equal to 1 to say j number of them is first order. So we write in this way 1 plus b I z inverse and 1 plus a I z inverse. So this is the first order, and the second order, say starting from equal to j plus 1 to say p number of them. So as it is mentioned here, up to p, and there is a second order. So 1 plus ei z inverse plus fi z to the power minus 2 divided by 1 plus ci z inverse plus di z to the power minus 2. And these are just coefficients of the numerator and the denominator. We don't have to take them too seriously. So you can vary numbers. So now in the series programming, how can I actually the method we have adopted for the standard program, the same thing goes. So basically y z by xz will be written as 1 plus biz inverse 1 plus aiz inverse, and then this one will be actually just like the standard programming. This one will be divided in this way: y z by hz into hz by xz, which will be equal to 1 by plus pi z inverse by 1 plus ai z inverse. Okay, so similar way we have to implement it. But if you look at the parallel programming, the standard programming, then you can see that these are actually the feedback that is coming. So this is forward, this is feed forward, this is feedback. So how many delay element you need? Definitely you just need one delay element. Okay, so X is coming as the input. Then there will be summing junction. In the summing junction, you're going to get your HHZ. Okay, so this is where you're going to get your HZ. So now from the HZ, you will have the feedback of this one with minus AI. So the feedback is going here with minus AI. So minus will be actually put inside here, plus here with the AI. Then this is your feedback, and then your output will be basically one. We are taking this one with this one, so ultimately your output YZ will be HZ plus B1 Z inverse HZ. So HZ is already there, so you can just take that one as it is, HZ, and the delayed one of the HZ, that will be multiplied with your BI. So these two will be grouped together as a summing junction with plus both of them. Then you're going to get your YZ. So bottom line is the numerator, the denominator is just the feedback one, and the numerator is just going forward, feed forward. Okay, so based on that, actually, you can also see how this one works. Okay, so as you can see, there is two delay element, 1 and 2. So we can just give two delay elements with Z inverse, the first one, the second one. Okay, so and X is going to the summing junction. So this is your XZ. And now this is your HZ. So what you can see is that the output will be HZ into C1 Z inverse HZ into D1 Z inverse HZ. So if you want to take the output, this will be actually your DI. Then it will be going to the final summing junction. Then from here you will have your CI. Okay. Sorry, it has to be forward, feed forward. So those will be basically the upper ones. So this has to be FI. Okay, and this one will be your EI. Okay, and directly HZ will also come here. So all of them will be additive. Eventually, this will give you YZ. And whatever the feedback, as it says that the denominator will be feedback with negative. So negative sign. So the first one is basically CI. So this one will be your CI. Definitely negative sign. And the second one will be your DI. Okay, so first order and the second order. So the whole pulse transfer function is to be transcated as a series of first and the second one. In this way, the error that is arising because of the quantization of the i's and the z's can be minimized. And if you look at carefully, you don't have to actually follow the step every time. Rather, you just by looking at the pattern, will be able to find out the way how to design it. Now, the next one is a parallel programming. The parallel programming, actually, the pulse transfer function G of Z is been expanded as a combination of A plus G1Z plus G2Z and goes on up to, say, GQZ. So as a total of Q plus 1 is because Q1 to G1 to GQ is Q number, and then for one constant you have a Q number. Basically, we are using the partial fraction expansion. Okay, so a combination again first and second order. So the A is just a constant, so keep it as it is, and maybe your summation of I equal to 1 to J. These are of first order, so BI by 1 plus AI Z inverse, and then plus summation I equal to J plus 1 to Q number in total. So EI plus FI Z inverse divided by 1 plus CI Z inverse plus DI Z inverse. Now, again, the question is how to represent them. Okay, so as we already said, the the denominator is going to be the feedback, and how many delay element is required here? Only one. So one delay element, Z inverse, then X is coming as the input summing junction that is giving you HZ. So you're going to find HZ here, and your output is only just BI. So HZ will be simply multiplied with BI to figure out your output. And the feedback is with a delay with a AI amount multiplied with the magnitude AI, then you'll have a negative feedback again. Okay, so this is your X, Z, and the output will be just a multiplication with BI will give you the result, that is YZ. So sometimes you can also express in XK and YK. So it's also okay to represent in the discrete zone. So similarly, how can we write this one? So similar idea, input X goes and you find the output H here, then HZ, and then how many delay element you need? So in total you need 2, so you just give 2, but for the output you need only 1. So then for the output EI, so EI is multiplied EI directly, and then the other one will be just multiplied with FI, and these two will be going to form the output. So this is your Y, Z, or YK. And the first one is feedback from your CI, okay, negative feedback, and the second one with DI. Okay, so negative, negative. This is your XK or XZ. Okay, so this is how you figure out in the first order block diagram, you figure out second order block diagram. So bottom line, the first thing you should do is whatever the pulse transfer function is given, you organize that as a combination of partial fraction expansioners like this, and then try to distribute them in terms of few first order and few second order pulse transfer function. In this way, the quantization error of your yeah, AIs and BIs can be minimized a bit. Now the third one that we have, and if you actually try to look at the series, the parallel one, how it should look like overall, then you can have a pattern like this. So your X, then you have A, then you have G1, Z, G2Z, and goes on up to GQZ. Okay, so combination of them, the summation in the output will give you the overall result. So this is your Y, Z, or YK. So first looking good, you can give it here, but eventually it is the same thing, XK or XZ. Okay, so this is how it should look. So individually, the first and the second order blocks will be replacing in this zone. Now the third standard method that we have is known as ladder programming. Slightly complicated, the ladder programming than the other two are reasonably straightforward. So the bottom line is how to represent is you have to expand the pulse transfer function into the following continued fraction form. So continued fraction form. Okay, so whatever gz is given, you have to try to organize gz as a combination of a0 plus 1 by b1z plus 1 by a1 plus 1 by b2z plus, okay, so this thing will continue until you reach a n minus 1 plus 1 by bn z plus 1 by an. So a continued fraction form like this you have to generate from the pulse transfer function that is given to you. Okay, so it seems complicated a bit. And we also have to define that what is gi in the ith stage of b function bz. So how can you define that? The ith state, that is in the first state. So first state is this one first. Then you will have gi of the next, gia of the next. So we can write in this way, equal to 1 by b I z plus g I a z. Okay, so this is I the b function of the ith one, which is having bi here and gi of the a function as well. So now what is gia? Z is basically 1 by ai plus next b function. So basically gi plus 1 b z. So the ith function here, ai, is considering with the function that is involved with 2. So that is why I plus 1 here. Okay, and finally gn b z. So b function, so 1 by, I think you can already guess, b n z plus 1 by an. Okay, so this is how you have to find the continued fraction form. So to make it more understandable, so say that we have n equal to 2. So if n equal to 2, what will be our gz? Gz will have a form like this. A0, starting from A0 plus 1 by B1 z plus 1 by A1 plus 1 by B2 z plus 1 by A2, because we are going up to n. So this is n equal to 2. Okay, so this is the one that we can figure out. Now we can, with the help of GI1. So what is our, with the help of the combination of GI a function of Z, sorry, G1, then G1B of Z, as well as G2B of Z. With the help of that one, we can just rewrite that one into a form like this. So what I can do here is, say here, this one can be this one, the whole thing can be written as G2BZ. So what you can write here is A0 plus 1 by B1Z plus 1 by A1 plus G2BZ. Okay, so next, this thing is basically nothing but your G1A function. So we can further write it in this way, plus 1 by B1Z plus G1AZ. Finally, what you can do is this thing is nothing but your G1B function. So A0 plus G1BZ. Okay, so this is how you have to make the form of your continual uh, fraction expansion. Okay, so now similarly, if you want to look how to represent them, so say we have GIB, GIBZ is a function, and we can say that at any particular point the output by input is related to this one. Okay, and that is given by 1 by, we know that BIZ plus GIAZ. Okay, so how can we relate, find out the corresponding block diagram from this one? So we just cross multiply. So what we can find is X, I, Z minus GIA Z into YIZ is equal to BIZ YIZ. Okay, so we are interested about YIZ output. So we can just say that 1 by BI, which is a constant, and then Z inverse, that is delay, with your XIZ minus GIAZ YI. Okay, so now how can you represent it? Very simple. You need to multiply with 1 by BI, then you have to give a delay Z inverse, and then you're going to get your output YIZ. Now in the input side, what will happen? The input has to be subtracted with this feedback. So input is XI Z, and with multiplication and the delay, now you need just to multiply with the output with just the gain, that is GIAZ. So once you multiply with that and give you a negative feedback, then you can easily represent the block diagram. Okay, so this is how we can represent. So basically, a gain is there, and a delay is there, and the next gain will be actually added there. Similarly, if we want to represent the GIA, so GIA function, how to represent that? GIAZ at any particular output or a particular input, we can write in this way: 1 by AI plus GI1. That is the next B value with Z. Okay, so we don't have to actually find this thing again and again, but it is always better to start from where we left off. So if you want to figure out AI YIZ equal to XI Z minus GI plus 1B, the next B function with your YIZ. So basically this is nothing but feedback again. So we said that this is nothing but feedback previously as well in the standard programming. So YIZ is basically 1 by AI, and then you subtract from the input the feedback of next B function with yiz. Okay, so how to represent it? Very simple. You need the feedback, multiply with only the gain AI. So this is your output. From the output, take a feedback of your next B function, gi plus 1, B into Z. Okay, so this one is slightly complicated, the ladder programming. The other two are relatively easier. So X, I, Z, this is Y, I, Z. Now, the ladder programming that we have done for two stage, I will try to implement using these two block diagram. This is for AI function, A function, and this is for B function. So in the B function, as you can see, gain is multiplied with a delay, and in the A function, only a gain is multiplied, then the next function is going there. Okay, so let's see how we can represent that. So we already figured out this. The G Z is A0 plus 1 by B1Z plus 1 by A1 plus 1 by B2Z plus 1 by A2. Okay, so from that one, we have seen that this can be written as 1 A0 plus 1 by B1 Z plus 1 by A1 plus G2 BZ. Okay, so in the next step, we have seen that it can also be further reduced as A0 plus 1 by B1Z plus G1AZ. Further, A0 plus G2 BZ. Okay, so, and this is finally is related to your overall output by overall input. Okay, so then you have your output input, that is X, then there is a summation block is going. So two signal will be going. One is directly going to A0, no question about it. And the other one is going to the block G2BZ. Okay, so those two are going to a summing junction here, and they are additive in nature, so both will be added together. This is your input XZ, and this is your output YZ. Okay, so now your this has to be G1, because already we have taken 2 here. So this is G1. So now how can we represent G1? We can see that in G1 can be represented by the fact that we have to divide by the B1, 1 by B1, and then we have to multiply with the next gain in the feedback. So what you can see is that this block here, we are just giving it terminal 1, and this is your terminal 2. So terminal 1 will be going from 1 by B1, and then a delay, because B elements need a delay, and then a feedback of the next one. So the feedback of the next one is basically your G1AZ. Okay. So the feedback is coming, then this is your negative feedback, and this is how this is connected. So this is your input. So basically this is your point A, which is same as this one, and this is your point 2. Okay, next is how to represent this one. So next step, we can call this one as a terminal 3, and this is a terminal 4. So we know that a function is only multiplied with a, and the direction here is of the block is here in this direction. So we have to give the a also a direction something like this, and which is a function and g1. So basically it will be divided by a1. So it will be going that way, and then you will have the feedback of the next one as well. So from the output, you have to take the feedback of the next one, which is G to B Z. And eventually that will go into a summing junction here. Okay, so this is your terminal 4 and this is your terminal 3. Okay, so last thing that you have to do is you have to take another terminal here, 5 and 6. And the direction is definitely in this way. So divided by the next B, that is 1 by B2, and then a delay, that is Z inverse. Okay, then you will have another feedback. And finally, this is only the last element. So it will be 1 by A2. Okay, so the feedback will be requiring a summing junction. So this is what we are going to get. So this is your 5 and this is your 6. So basically how we are going to connect it. So connection is very, very simple. You just connect one with one and you have to eliminate the, let me use the eraser a bit. So we have to eliminate this branch. Okay, and then we have to connect these two branches together. So this is your 1, and you have to connect these two branches together. Okay, so one branch is going up the signal and the other branch is going down. Then the 3 and the 4, you also have to connect those. So let me erase that one. Actually, it would have been better if we could have drawn one under the another one. Okay. Okay, so 3 will be connected with this 3 and the 4 will be connected with this 4. Similarly, your this block, okay, so this block will also be removed and eventually you have to connect these two. So just connect these two, nothing else. So one will be going in that direction and the other one will be going in that direction. So just look at the book example. I just make the thing a bit complicated by removing the figure into the other side. So basically this is your page figure, book figure 342. So the ladder programming is slightly complicated, but the other two were reasonably simpler. So I think you better look at the book example for this one. The last topic of this chapter is the infinite response filter and finite response filter. So before that, you try to look at the example, I think 3.8. So series, parallel, and ladder programming is given in example 3.8. So it will help you to understand more clearly with some practical values how to design the thing. So now, last thing that you should know, infinite impulse response filter and finite impulse response filter. So whatever we have figured out so far, YZ by XZ with B0 plus goes on to up to A1 plus A1, and this goes on. So Z inverse. Okay, so this is what is called, it needs infinite number of samples. That is why this is called infinite response filter. Also, it takes the present and the future values of your input. present and the past values of the input as well as past values of the output to calculate the present value. Basically, it can be cleared from the fact that if you just take it into the difference equation, the difference equation of this one, then you're going to say that yk equal to minus a1 yk minus 1, which is the past value of the output, minus a2 yk minus 2, minus goes up to minus an yk minus n, plus b0 xk. This is present value of the input and also the past values xk minus 1, and goes up to bm as xk minus n. So the present output is dependent on past outputs and present input and past input. So this is why it is also known as a recursive filter. Recursive filter. Okay, so because of the recursive nature, in the output, if you are in the previous output, if you have errors, so all the errors will also be accumulated. So this is infinite sample or infinite impulse response filter, or it is also known as recursive filter. On the other hand, there is another filter with, in the previous one, as you can see, both A and B are present. Okay, so both are present, and this will give you the indication that it is a recursive or infinite impulse response filter. Whereas the other one that you have, the other one, we just have only the B term. So yz by xz equal to b0 plus b1 z inverse goes on up to bm z to the power minus m. So in the difference equation form, you're going to see that yk, which is output, current output, is basically a function of b0 xk, so present input, and past inputs, xk minus 1 goes up to bmxk minus m. So this is, the length is finite. It can be limited to your number of the zeros, or even if you want to make it even smaller, you can reduce that. And because of that, it is also known as finite impulse response filter. And also, as you can see, it doesn't depend on your previous outputs. It is also known as non-recursive filter. Non-recursive filter or moving average filter. Okay, so how can we realize the finite impulse response filter? Realization of finite impulse response filter. Realization of finite impulse response filter. Okay, so we know that output, the convolution summation that we have let you to derive in the last, one of the last class, is just the summation of h equal to 0 to k sample is g ht, then delayed version of your input, that is xkt minus ht. Okay, so this is a convolution summation. If you just expand it, then it is waiting sequence is your g with current value, then the next waiting sequence and the previous values of your input, and goes on up to the last waiting sequence with the initial, the first value of your input. So this is how we can write it. Now again, to find out the output from huge number of past inputs can be a difficult task for the processor, as well as you need a huge number of memory to process that one. So that is why instead of taking all the previous inputs, it is wise to take n immediate sample and immediate samples, significant ones, as long as it is significant. So now you can write your ykt as with g0 x the present input plus gt x k minus 1 t goes up to the nth. So g and t x k minus n t. Okay, so we are just truncating some of the inputs so that the processing doesn't delay enough. Now, how can we represent this one? Now, if you go into the z plane, so represent this one is very, very simple. Yz equal to g's are just weighting function, the magnitudes. We don't have to bother about that one. So g magnitudes with the delayed version of our input xz. Okay, so that goes up to g and t to z to the power minus n xz. Okay, so we can just implement this one using the block diagram. So z inverse delays goes on up to how many? Nth number of it, z to the minus n. So nth one will be multiplied with g and t magnitude or gain. The first one is multiplied with g0. So first one is multiplied with g0. Second one is multiplied with gt. Third one is multiplied with g twice t. So goes on. So all these will be summing together. All these will be summing together to give you your final value yz or yk. So this is your xk or xz. Okay, so this is the realization or block diagram realization of a non-recursive or a moving average filter with n intermediate terms. Okay, so you just have a look at the summary of this implementation that will give you a even better picture, and also look at your example 3.9. So deliberately in the example 3.9, a pulse transfer function is given, which is 2 minus 0.6 z inverse by 1 plus 0.5 z inverse. So if you just divide it, and we know that this is just output by input, and deliberately they have said that your input is a delta, Kronecker delta function. So basically the magnitude is 1. So whatever you are going to get by dividing these two number, so if you divide 2 minus 0.6 z inverse with this number 1 plus 0.5 z inverse, so you're going to find a series. In that particular series, since it's a Kronecker delta function, each individual sample will be the value, because x0 is only having magnitude 1. So at that particular sample, only that particular one is your output. So in the next sample, this one is the output. So if you just have a look at that one, you'll realize that if you just divide these two, whatever the sequence you're going to get, that is eventually your final response. Okay, so if you have any question, we can discuss in the class. Otherwise, let me stop here. Assalamu alaikum, everyone.